Okay, so I'm recording a video to show how to work this quiz which I gave as an optional quiz a couple weeks ago. This is quiz 2, chemistry 1212, and I'm going to work solutions for it. And the front page looks like this. But I'm going to go over my sketchbook here because it makes nicer. It makes nicer. Um, you can see it better. Okay, so let me bring this here. This is question 1. And this is like the question that I did in a video where I solved the problem 13.2. I posted a video a couple weeks ago, and it's chapter 13, probably section 2 or 3, I forget. But it's essentially the same kind of problem. So if you want a better solution, a more thorough solution, then consider going back and looking at that. I'm going to go kind of fast here. So determine the rate law and the value of K for the following reaction using the data provided. So the rate law is going to look something like this. Rate is equal to K, concentration of, let's see, A, B, right? A to the X, B to the Y, right? Rate laws always look like that. So if this is A and this is B, in a minute I'll put more details in there. I can see that after the first two trials, or for the first two trials, A does not change, but B doubles. And since B doubles, I can see that, so it's going to be like this. A, right, is equal to those ratios there. Since B doubles and the rate doubles, it looks like Y is going to equal to 1. Right? Can you see that? This is going to go to 1 no matter what. And so if this is 1/2 and this is 1/2, then Y to the 1/2 gives you 1/2. I'm sorry, this to the 1/2 gives you 1/2. So as I said, if you want a more thorough explanation, you're going to have to go to another video to look at it. All right, now I'm going to look past the red. I'm just going to do black. And can you see that this is, there's 1. This is just 1, so that's going to go away. And this is 0.1 over 25, which is 0.4. 0.4 raised to the x gives you, and that comes out to also 0.4. 0.4. If you divide those two, you see it. So can you see that x is going to be 1 as well? X is 1 as well. All right, so if that's the case, then the rate, let's go on to, we know this. The rate is equal to K, A. I'm going to go ahead and put what A is in now, okay? It's NO2 raised to the 1. Ozone raised to the 1, right? And so let's take a specific example of that. Let's just take the first row. 1.42, can you see that? Oh, that's why people got that wrong. Look at that. It's supposed to be molars per second, not reciprocal molars per second. A lot of people got that wrong. That's the reason why right there. I didn't realize it was wrong in the exam. I'll have to go back and add that to your scores. Is equal to K, and the concentration of NO2 for this first trial is 0.1, and the concentration of ozone for this trial is 0.33. Right? So K is equal to 1.42 over 0.1 over 0.33. I have my calculator here. Hope you do too. 1.42 divided by 0.1 divided by 0.33. And it comes out to 43.03. Equals 43.03. And this should be molars per second, but this says reciprocal molars, reciprocal seconds. I'm going to put molars per second, even though that is wrong. Okay? So this is the way it ought to be. A bunch of people put the units as they were here, and I took off of that. I'll have to go back and change those scores. All right, so let's look at the next problem. Don't save. File, add image. Number 2, open. Okay, so the rate constant for the first order decomposition of N2O is blank. 3.40 reciprocal seconds. What's the half-life? Oh yeah, okay. So half-life, and if it's first order, then half-life is equal to the natural log of 2 over k, right? So this is going to be 0.693. I have that memorized, but I'm going to calculate. I've got my calculator here, so I'm just going to go ahead and do it. Natural log of 2 is equal to 0.693. I'm going to add another sig figure. 1 over 3.4 reciprocal seconds. So it's going to be seconds. Can you see that? Okay. Divided by 3.4 equals 0.2039. 0.2039 seconds. And this has got 3 sig figs in it, so I'm going to say this is equivalent to 0.204 seconds. And by the way, this one is has a problem like it. This is on page 534, and it's example 13.6. I did this in a different video also, so if you want more time on that, go back and look at that video, which I posted a couple weeks ago, for the section that has example 13.6 in it. Okay, next problem. Save, file, add image, 3. Okay, yeah. Which of the following statements is false? Alright, so we know that K is equal to the products over the reactants, right? So when K is very big, it says the forward reaction is favored and essentially goes to completion, and that's true. But we're looking for what's false. So it's not the first one, because that's true. When K is very small, the reverse reaction is favored and the forward reaction essentially doesn't go forward, and that's also true, so I'm going to mark it off, right? When K is about 1, oops, that's supposed to be concentration, neither the forward reaction nor the reverse is strongly favored, and about the same reactants as products exist. Yeah, that's true. Can you see that? If these are both about equal to each other, K is going to be 1. So I'm going to say, nah, that's also true, so it's not false, right? Okay, and K being greater than 1 implies that the reaction is very fast. This says nothing about speed. K says nothing about speed. This is question number 3. There's a note that says essentially to this effect on page 586 intro. If you want more on that, please go to page 586 and have a look at that. Okay, number 4. Determine the value of Kc for the following reaction. Alright, yeah. So this is like page 570, example 14.2. I also did a video on this. I don't know what video number it was, but it would be the section that contains that example. So if you want a slower, more clear explanation, please go to that video. Okay, so determine the value of Kc. So K is equal to the products over reactants, right? Well, here's the products, and that's squared. Right, and here's the reactants. Agreed? And that's K. So I'm just going to go ahead and put those numbers in there and calculate it. The HI is 1.6 squared, and H2 is 0.14. Can you read my writing? A little too small. And this is 0.39. Okay, so this is going to be 1.6, just a second here. 1.6 squared divided by 0.14 divided by, oops, just a minute here, I did the wrong thing. 1.6 squared divided by 0.14 divided by 0.39 is equal to 46.886. 46.886, which, if we're doing this to 2 sig figs, right? See how those are 2 sig figs? this is going to be about 47. And there are no units here. Okay? So I don't think I took points off if you put units. I don't think I did. Probably should have. So if I did, then that's the reason why. Because K has no units. All right. And then add image. Number 5. Okay. Oops. Whoa. Okay, so this is like the example that's done on page 578. I also did a video of this one in advance of this quiz. Example 14.7. And again, whatever video has that example in it, or whatever section has that example in it, I've got a video that's named after it. So, okay, consider the following reaction and its equilibrium constant. K is such and such, all right? So if K is such and such, the reaction mixture contains blank. Ah, okay. So if we're looking for what's going to happen, is it at equilibrium or not? We got to calculate Q first, and Q is equal to products over reactants. You know what I'm going to do? I'm going to do this in black. I'll give it the previous one. Q is equal to products over reactants, and so it looks like it's, and neither of those are squared, right? And they're all gases. There's no heterogeneous equilibria, no pure liquids or solids, so it's going to be that, all right? So let's do SO3 first. SO3 is right here, 0.11, and then we'll do NO is next. Let's do it there. It's 0.14, right there, okay? And then on the bottom is SO2, which is 0.39, 0.39, and then this NO2 is right here, right? 0.14. Oh, look at that. Those two are going to cancel. So this is going to come out to be 0.11 over 0.11 divided by 0.39, which is 0.282. 0.282. That's the reaction quotient. That's where it currently is. Now it looks like if K is 0.33, then this is too small. Not enough products, okay? So the reaction will shift in the direction of the reactants? No. Oh, we are looking for something that's true. You see that? The equilibrium constant will decrease. No, a constant is constant at a particular temperature. This says nothing about a temperature change. The reaction will shift in the direction of the products. Aha, that's it. The reaction quotient will decrease. No, it's got to increase to get to equilibrium, right? It's got to get bigger. It's not that. And the system is at equilibrium. No, it's not that. It's C. The answer is C. And I know this is a little bit busy, a little bit fast, but if you want a better explanation of that, please go to page 578 and look at Tro's solution, or look at my video that contains example 14.7. All right, I hope that's helpful.